Does it record our questions too, I guess?
What's that, Travis?
Does it record things that we ask and stuff, I guess, too?
It's just recording our Zoom session. So it just recorded what you just asked. It's recording what I'm answering right now.
Okay, I won't ask anything too dumb then.
It'll be recorded. But no one else is going to watch it, though. So for us.
Okay.
I don't have much of a YouTube following. Embarrassment of my almost 11-year-old son. I'm a YouTuber, but I think I have 2 subscribers. Okay.
We'll subscribe to you, Carl. Don't worry.
It's not super thrilling, but okay. What I wanted to do today was go over that practice midterm. And particularly, I think it'd be better to start backwards, because I feel like that might be where the more, most of the questions are revolving around. So the mechanisms and the products. I feel like you probably have a decent handle on the nomenclature. And so in terms of drawing the structures and stuff like that, if there's time, we can get to that later on. But I think it's better use of our time, and I'm not sure how long it will take to go over those things toward the back. Now, if you look at Canvas, and apologies, I do have my assistant here. She is, say hi, Nora. Yeah.
Hi.
Hi.
So, despite vomiting in her crib last night, which that was my Valentine's Day present, I came in and she had thrown up everywhere.
Nothing but love.
Yeah, she seems to be pretty fine right now. But I just can't. Oh, now you're writing on your face. So anyway, I apologize in advance for the distractions. I might have to get up and get her things and stuff, but
it's okay.
Bear with me. And
doesn't bother me.
I have to call off work, so I'm just doing this because I don't want to leave you guys in the dark on what to expect for the midterm.
We appreciate it.
Yep.
All right. So if you go to here you want to raise it. You go to week 6. I've posted several things. I've created a slide deck that just compiles all of the slide decks that we've had this quarter, and I've taken out some of the fluff. So it's a condensed version of the slide deck that you can scroll through more easily if you want to review certain mechanisms.
Okay.
There's also this OChem reactions Excel, and so when I click on that, can you see that?
Yes.
Okay. So, I've compiled my own, here's a list here that has the different types of categories and what the reactions are called. And, if you have an alkene or an alkyne, and then the reactants. It'll also tell you some things about Markovnikov or anti. And so I have encouraged you all to make your own lists and things, but if you want to review this as well, you can.
Thanks, Carl. That's super nice.
Yeah, you're welcome. Trying to give you as many resources to prepare you as possible. And then also, I have uploaded the midterm practice key with all the answers. So what I suggest is that you continue to practice this exam and then check, fill it all out and then check your answers and see how you get. The exam itself on Thursday is going to be the exact same format as this with just, slightly different molecules. Maybe the mechanism toward the mechanisms toward the end might be different. Instead of NBS, it might be something else. But this should give you a good idea of what to expect. If you do decently well on this practice, you'll do decently well on the actual midterm. Yes. Yeah. Okay. What do you want? Okay. So why don't we get started, and let me share the midterm here. I do have my whiteboard, but I think with the glare and the lights and stuff, it might be easier just for me to attempt to write, to annotate on here. And then maybe I'll just pull up the key itself with the answers, and we'll see how well I am at dusting off my Zoom skills. It's been, it's been a year and a half or so since we had the luxury of experiencing education without the restriction of wearing pants. So here we are. I'm wearing pants and Nora's wearing pants. She's just not wearing a shirt. Okay, so let's get started. Like I said, I really kind of think that this stuff is pretty straightforward. Again, the answers are on Canvas, and if there are any questions about that, if we don't get to this section, shoot me a message on Canvas, and I'll do my best to help you with that.
Okay.
What I really want to focus on is this stuff here. Okay.
Okay.
Okay. And then we'll backtrack as we can and see how far we get. Yes.
So you don't want to start at the very end? Do you want to start on the predicting the?
I'm happy to start wherever. I mean, this is your review, so we can kind of warm up with these reactions and then get to mechanisms. That's what I was going to think.
Sure.
Okay. All right. So when you see NBS, right, and you see heat and light, what that should trigger in your mind is an allylic bromination, right?
Right.
So go to the slide deck that I compiled. Yeah. It's right here. Allylic right here. Oop, one way. Right here, right? Allylic bromination. So what that's going to do is that's going to prevent the bromines from attacking the double bond, right? Because we only have free radicals that are produced. We don't have also in that environment the liquid bromine, the BR2.
Mm-hmm.
So actually, I think the practice is this is exactly the same molecule that I used for the mechanism later on. But essentially what that is going to look like is, yes, let's go back here and let's get our annotation. What that's going to look like is, hi. Sorry, that hopefully they'll get better over time. Right, we have that. And then we are just going to put the bromine on that allylic carbon, right? The carbon next to that double bond.
Right.
And of course, we'll have enantiomers with that, right? So we'd write EN, because this could be a dash instead of a wedge, right?
Mm-hmm.
And of course, if we put it here, if we were to put it right here, that's the same molecule, right? We've just flipped it upside down.
Yeah.
So the second one, O3, when you see O3, that should trigger in your mind ozonolysis, right?
Right.
This is ozonolysis with an alkyne, okay? And so when you have ozonolysis with alkynes, you end up with carboxylic acids, okay?
When it says DMS though, so many examples that I'm seeing online just use O3 and then or ozone and then water. And and DMS can be used like it's basically the same thing, I guess. I mean, I know it's not the same thing as water, but
yeah. So it stabilizes the reactants. So if you use water, you could get that could interact with the ozone. The DMS just is kind of like a preservative in a way. Okay.
Okay.
It's there so that the ozone can attack the molecule that you want it to.
Okay. All right. And not like escape into the atmosphere or something, I guess, or whatever. Okay. All right. So then we don't really need to worry about the DMS then. We're just worried about the ozone.
Yeah. I mean, for the purposes of this, because you're just writing the product, the DMS is going to add to that molecule.
Yeah, okay, yeah. If we were doing the mechanism, then we might have to.
And so, again, if that is we're going to essentially break those double bonds, right? And we're going to end up with carboxylic acid. Okay. And we'll also have CO2 in there as well.
So that's if it's a terminal alkyne, right? And if it's not a terminal alkyne, then we make 2 carboxylic acids.
Yeah, it's gonna break them apart.
Okay. And then it'll just be 2 different ones. And then there might be different R groups on each side. So they could be different molecules, I guess, but they'll both have a carboxylic acid on either end, I guess.
Yes.
Okay.
We're alkynes, right?
2 alkynes, yeah.
So let me see if we have an alkene example. Yeah, so there is an alkene example further down where it's going to be ketones. We're gonna break those apart and form 2 ketones using
yeah.
alkene, not an alkyne.
Okay, yeah.
So that's again, when you're memorizing these mechanisms and you see O3, that's ozonolysis, but then you got to see what type of molecule you're using that on, right? If it's alkyne, think carboxylic acid. If it's alkene, remember
ketones.
So now, what do we have here? What does this tell you when you see these reagents? What does that indicate? What kind of reaction?
So the mercury acid catalyst?
That's an alkoxymercuration, right?
Yeah, oxymercuration acid catalyst. You're both right. Right? Because it has this mercury here and it has this acetate. And so, come on now. What we're going to, for some reason, it's not wanting to let me.
The way I've been memorizing it is that there's oxymercuration, then there's alkoxymercuration, right? And so there's an alcohol group on there, so that's alkoxymercuration.
Exactly. So if there weren't that ethanol there, it'd be different, right? We would just tack on the oxygen and an OH and a hydrogen. But since we have the ethanol there, exactly. So we have our methyl group come back here. And then what that's going to do is it's going to give us the oxygen and then the ethyl group.
Okay, yeah.
And why is it here? Because remember, it's Markovnikov and there's no rearrangement. Okay, so if we're looking at this double bond here, that double bond breaks where is that oxygen going to go? It's going to go to whatever is most substituted. And this carbon here is tertiary. This carbon here is secondary. So that's why we tack it onto the methyl group, or the carbon that has the methyl group.
Right.
And so if we have an alcohol group that we're using as our reactants there, then that gives us an ether. And if we have water, then that gives us an alcohol.
Yeah, right. Because this is an oxygen that is bound to R groups. Yes. Hi. So it's an ether.
Cool. Okay.
Yep.
Cool.
If there is no, so and if that was MEOH, right, then it would be an ethyl group instead of an ethyl group, right? So, or if it was propanol, it would have one more carbon on it. So just be alert for what is, and that's kind of why I highlighted that in red there. Be alert for what is coming along with that oxymercuration.
Okay.
Perfect.
All right. What else? Let's see. Sweet. Okay, so what do we have going on here? We have sulfuric acid.
So whenever we see sulfuric acid and water, we could think H3O plus, right?
Yes, we write H3O plus. If the H2SO4 isn't there, what you want to see is when you see acid, you want to think acid catalyzed hydration.
Okay. And then all of that, there's no steps there. There's no steps 1 or 2 on this number 4 here. So all of that is in the same solution altogether, right? I mean, I guess it's not relevant to this, but I mean, does that matter?
Not for this part. For this part, you're just drawing out the products.
Yeah.
Or draw the mechanism and show the push arrows like later on. It's all the reactions happen sequentially, right? So
yeah,
we want it to be in a stepwise manner.
Yeah.
So what is this going to look like? We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And the double bond is right here. Okay, so I'm just taking that and turning it into a skeletal structure.
Yeah, that's what I did with mine.
Okay. And we're going to end up, because it's an alkyne, we're going to end up putting an alcohol on there and creating ketones. Okay.
Right.
But with this, we could have it in 2 different spots. As a rearrangement, we could put it here, or we would have it on the other double bond.
Oh, yeah. Okay. So that brings me to my question then that I had written down about this, because I was going over this with the tutor. And so is one of those the major product? Is that the major product then? The one that's on this, well, they're both the same, right? I mean,
in terms of the carbon, they're both secondary.
Yeah. But when you're asking to draw, well, okay, so you say draw the major product for each reaction. Okay, so and if they're expected in approximately equal amounts, then draw both products. So they're probably expected in equal amounts, I guess, right? Kind of.
Yep.
Okay.
Okay. So we have those 2 happening, and then the next one, this is kind of a reverse process, and what we're doing is this is going to be for preparing an alkyne. All right. We go back to the slide deck. I've learned that Expo, dry eraser doesn't come out of sight. Okay, where were we talking about the alkynes? Right, so if we have an alkyl halide and we put it in the presence of excess sodium amide or amide, we form an alkyne, right? And we can then continue because it's in excess. Hey, Ian, can you hear us?
Yes, I can.
Sorry for the pivot onto Zoom. We are just going over some of the reactions in section 2 on the practice midterm. You haven't missed much. And I've posted the key to Canvas week 6. So, and once I'm done with the Zoom, I'm recording it. I will send a link to YouTube once it's uploaded, so you can catch up on anything you may have missed.
Okay.
So we are currently on page 5, at the very bottom of page 5 on the practice midterm, and we're talking about making alkynes in the presence of excess sodium amide. And so we create ethylene, right, or acetylene, and then we can deprotonate it with excess sodium amide and form the acetylide ion. Okay, so that is what we're going to do with this.
Then we're adding an ethyl.
And then we're adding an ethyl, exactly. Okay.
And it's Markov.
Yep, and there's no poison catalyst here, right? So, if you saw the poison catalyst on there, or Lindlar's catalyst, it would be a different approach, right? That's how we can partial hydrogenation. There it is. Okay. Down here. So if we are to figure out what's going on with this, right? The bromines are going to come off, right? And that bond is going to then form up here. And then another bromine is going to come off. But,
I kind of have a question on this.
Sure.
If you don't mind. So it's a little weird to me how there's a methyl group and then the bromine attached to it on the bottom there, the branch, because I know this is going to turn into alkyne. And so that branch seems like it's going to get in the way of the methyl group of like compressing it all. Because I see I don't know, it's just, I guess I don't need to worry about the mechanism of it, but.
No, but you do need to know what you precisely just said, that what happens when we do that. This bromine here can only go onto this carbon here, that, or not the bromine, but the bond, right?
Mm-hmm.
There. And so this one then will also go there.
Mm-hmm.
But now what's the problem with that? We have this methyl here. So that's going to undergo a methyl shift.
Mm-hmm.
Okay. Oh, okay.
So that's a tricky one. Okay.
Yeah, that's what's throwing me off.
And hydride shifts, right? Hydrogen's moving around and stuff, rearrangement. That has to happen in order to make this acetylene.
Mm-hmm.
Oh, okay. That's what we're making out of this is acetylene.
Yeah. So this is kind of a reverse process, right? Instead of starting with an alkyne,
Yeah.
An alkyl halide.
We're creating when.
So because NH2 is a really strong base, then that's going to be snatching away those bromines. And then that's what's going to snatch them away. And then those bonds are going to kind of collapse back onto the molecule.
Yeah.
In a way, if that's a way of thinking of it, I guess.
Yes. So it ends up looking like that methyl shift.
Yeah.
Yeah. And we can write the hydrogen in there.
Okay.
At that point. And so then in excess, right, we remove that hydrogen, right? And now we have, oh, okay, you want some water? We have an acetylide. I'm going to get her some water real quick. Okay. What I want you guys to do now is, where does it end? Now we have.
Well, we add the ethyl.
Yeah.
Where does it end?
Okay. Go. So.
You mean like the termination step or whatever?
Well, no, because that's with free radicals.
Oh, okay.
We just add the ethyl.
Right. So we're just simply add the ethyl group on there.
I figured so the bromine doesn't come along and snatch the hydrogen because that would make like an anion, I guess, right? So.
Well, I mean, if the bromine snatched the hydrogen, that would form HBr, right? Hydrobromic acid.
Yeah.
But this base is super strong, right? And it's going to be pulling that hydrogen off.
Oh, yeah. Okay, yeah. Okay.
All right, so now what we see here is, again, oxymercuration, right?
Mm-hmm.
So this, on the other hand, is with an alkene. And what do we know about that? No rearrangement, and it's marked off the top, right?
Yep.
Right.
We're going to hydrate it by putting the OH group on whatever is most substitute on that double bond. So if we're looking at the double bond,
It's a secondary.
which carbon is more substituted?
The secondary. So it's going to make a ketone.
Black or yellow, right? The black one. Yeah.
Black.
Yeah.
Mm-hmm.
Exactly. So let's write what that looks like here. So we've got our here, and then right there, we'll take the double bond off, and we're going to put, we can show, you know, our stoichiometry, or I'm sorry, our stereochemistry. We put the hydroxide group there. And if you wanted to, you could, you know, show the hydrogens here, although that's not necessary, right?
Yeah, because whenever we see a water, that makes alcohol. And whenever we see an alcohol, that makes an ether. Right?
Well, didn't you say for the oxymercuration, if it's with an alkene, it's going to create a ketone? And then if it's with an alkyne, it's going to create a carboxylic acid?
It's not creating a ketone here.
That's normally with that triple bond.
Yeah, so this, right?
Alkynes.
This is not a ketone, not a carboxylic acid, because it's an alcohol.
Oh, so when you said that earlier, it must have been, you're just talking about the double bonds. We switched that up.
I was talking about ozonolysis. Maybe well, it's recorded. We can look back and see. Maybe I meant ozonolysis. Maybe I also accidentally misspoke for.
Maybe you did. No, I think maybe because they were right next to each other, and I just wrote it in an area. It looked like
Yeah.
it was in the one of it.
Gotcha.
Or
so, right, this is hydration. We've got an oxygen, and then you'd want to add your enantiomer, right? Because that alcohol group would be a wedge or a dash.
Uh-huh.
Why is, oh, the joys of annotating on Zoom. Yes. Okay. What is the next one? We have BH.
The boron, anti-Markov.
What's that, Ian?
Anti-Markov.
Yeah, it's
Breaking.
And it's hydroboration oxidation, right? So yeah, when you see this stuff, you have borohydride and tetrahydrofuran in the presence of peroxide and a base, right? Think to yourself, hydroboration oxidation, anti-Markovnikov. That's going to be important because that's going to tell us, right, where.
And then we'll have an aldehyde, right, or something.
Yes, we'll make an aldehyde. So let's draw that here, and then we've got this one here. Yikes! Sorry. Right. So we've broken a double bond. We've added an oxygen, and remember we add we add alcohol. We create a bromine that's connected to 3 other alkyl molecules, and then the peroxide comes in and it sandwiches in between the bromine and the R group that it's connected to, and then the bromine gets trimmed off. And then we have an alcohol group, and then that H gets pulled off by the base. And I'm saying all this instead of writing it all because, for one, this problem doesn't require that. And for two, one of the mechanisms involves this process. So we'll visit it there, although it's not as complicated because it's using a different form of boron. But yeah, so let me try to draw that without a girl in my arms. And as Ian said, if we drew the H there,
we know
aldehyde. And notice it's on the less substituted carbon, right?
the ketone you'll know is formed if it's Markov, effectively.
Exactly. So if it were Markovnikov, it would say, oh, well, this one, that's secondary. So I'm going to put it here instead. And then actually that would, where's my eraser? I know it's here somewhere. There it is.
But these hydroborations are not, they're anti-Markovnikov, so we know that it goes on the end there.
It goes on the less substituted.
The less substituted carbon. Yeah.
That's going to be the tricky part for the exam, is just keeping track of all this stuff.
Yeah.
That is like I said, that's why.
Because it was with like the Hg squared thing, right, or something, to create the ketone one.
The
alkyne.
Well, that's HgOAC. That's what we have here. And let me get rid of this. I don't want this to confuse you.
Yeah, but that one's just an alkene reaction. Or yeah, it's not an alkyne.
This one here?
The
Oh,
top
the
one.
top 6.
What you
Yes.
said with the HG. But I think alkene ones have the squared, right? It's HG squared something. I don't remember off the top of my head.
For alkyne?
Uh,
Yes.
yeah, create the ketone.
Yes. I don't think there is an example. I don't think I have an example on here.
Phenol formation. HG, yeah, 2 plus or something. What was it?
Get to
HG2. Acid catalyzed hydration is slower than with an alkene, so HD2 plus, squared plus. Or I think that's its charge.
Yes, that'd be the charge.
HD2 plus.
Okay. Oh, so also, Ian, if you look at the week 6 Canvas page, I have the answer key for this, and I have an Excel spreadsheet where there are these reactions and what if they're addition or elimination, etc. For
nice, that's pretty much what I did.
Perfect.
I made like a very similar
and then there's
for my study.
Wonderful. That's what I was hoping you would all do. So, and then there's also a slide deck where I just compiled all the slide decks this quarter and just took out some of the stuff that was not, I hate to call it filler, but it's got just mainly the practice problems and the mechanisms. Okay, so it's kind of easier. You can just kind of scroll through there if you want to reference something without having to pull up all the different slide decks.
Yeah.
Okay. So now
we're adding BR.
Here, this is where we left off, right?
Yep.
Okay.
Then we got the aldehyde added.
So what's this?
Breaking the bond and adding 2 BRs.
Yeah. Hydrobromination.
Yeah, right? I don't know why that one was throwing me off so much. It just looked so different.
And it's not a free radical because we don't have the HV.
Yes.
Which it could be if it had the HV.
It's not a free radical. And, we usually do that in the context of alkynes here. But we don't have to, but here's an example of an alkene, right? With the NBS, which is going to cause that free radical. But here, no, when you just see Br2, it's hydrobromination, right? We're going to just add hydrogens on there. Or we're going to add bromines on there and hydrogens. It's Markovnikov, right?
Yeah.
So, yes, look what you've got here. Let me see if I can attempt to draw this.
Yeah, I'm trying to draw this.
Let's put this down here. Okay, and so
and this can be, the addition can be anyway, so it'd be plus an enantiomer.
Precisely.
Okay.
So you could just write it like this. Plus En. Or you could write one as wedge and one as dash.
True. Yeah.
And there's no platinum here, so it's not going to be a syn addition, but keep in mind that if we want to have a specific type of stereochemistry, then it gets more complicated, right? We can add more things to it to get that addition to make it a cis.
And if there was a platinum there or palladium or whatever, then that's just adding that's hydrogenation, right? That's just adding the hydrogens.
Yeah, but it would be from that coating of platinum or palladium, and so it would be a syn.
Yeah.
Okay. Okay, cool.
Okay, again, we see O3 and we think ozonolysis. We did it previously with the alkyne right here. And what did we get with that? We got an aldehyde, or carboxylic acid, sorry. Right? We do it with an alkene. We effectively break these two carbons apart and form
two different
ketones.
Yeah.
Okay. So ozonolysis with alkyne versus ozonolysis with an alkene. Right?
I saw a trick online where the lady just takes this molecule and then she draws a line through the double bonds and then writes an O on either side of that line.
Yeah.
And then that's a way of like seeing that there's two ketones going to be formed.
Yeah. So what I was going to do is not that, but I was going to just write it like this.
Yeah.
Right. And so, right.
Cool.
Okay. Some of these are simple. Some of these, you gotta kind of memorize it, but pretty straightforward. Some of these are a little bit more complicated. What's going on here? We have sodium and ammonia. We're going to get hydrogenation.
Yeah.
Okay.
You're breaking the bond and just adding H's.
Yes. And so we have.
But it's not in with platinum, so it's not with a syn addition then.
No, it'll end up being trans, right? So it'll
Yep.
look. Oops. Like this, right? So this methyl group is pointing down. This group here is pointing up. Okay.
So that's that it just takes off a bond.
Yeah.
It just makes an alkene from an alkyne to an alkene. It's just a reduction, I guess, or something.
Yeah.
Oh.
This is just hydrogenation.
That was way harder than when I was making it in my head. I mean, way easier than when I was making it in my head.
You're making it way harder.
Yeah.
Okay. Now we're going to get into the hard stuff, though, right? We have this mechanism, which, there's a lot going on there. And you haven't, I don't think we've even covered this right here, this R2BH, that's a dialkyl borane. We've always done it with BH3THF because we can't.
Yeah, I was gonna say this is a bore.
We can't possibly cover all of the reagents, which is why I threw this in here, because you may come across this if you take OChem somewhere else, or I don't know, maybe we'll revisit this reagent at some point. But
so anti-Markov. breaking the bond.
Anti-Markov,
We're going to have an
hydroboration,
aldehyde.
oxidation. Sorry.
We'll
Go
have
ahead.
an aldehyde at the end.
And I'm going to grab a cup of coffee. But then we have not acid catalyzed, but a base catalyzed reaction.
Through NaOH.
And then we have tautomerization. We have that enol tautomerization.
Yeah.
We're going to end up with an aldehyde. Okay, so a lot there, a lot to unravel. First, okay, let's talk about this dialkyl borate. You want up? So that is simply B. Yikes, there we go. B with one R group here. An R group here. And an H. So unlike BH3, it has those R groups. It's not going to give those R groups up to bind to some other R group, right? So it's a way to kind of circumvent that that binding of the three different target molecules onto one borane. We're still going to bind that H and that boron to that site of that alkyne.
Yeah.
And we are going to put in we're going to use the peroxide to put in that oxygen sandwich and everything else, right? But this is a little bit simpler. You don't have to draw out that, that intermediate there. Why do you have to be like this right when I'm getting into like the meat of the review, baby?
She was so happy the whole time. Now she's not.
So let's see where.
Formation right there.
Yeah.
Does the double bond snatch the hydrogen? Or the triple bond? I mean, does one of the bonds on the triple bond snatch the hydrogen? So we start off with that?
That alkyne is broken, and one bond. I'll get to that, but one.
Okay.
The boron binds to one part, and the hydrogen goes to the other side. Okay. And because it's anti-Markovnikov, the boron is going to go to the less substituted.
Okay. Yeah. Boron goes to less substituted.
Here we go.
That's it, effectively.
I know you're excited. Well, what happened? Oh, you know what? Because we talked about this in the context of alkenes too. So here. Right? So you touched something. So here, we're not going to do this part here where the boron, or, well, we can even step back right here, right? The part where the boron goes to three of those target molecules. We're just going to go to one. Okay. So it's simpler for you guys in that regard. So what does that look like? Let's draw this here. Let me get my annotation going again. What we have is have it like okay. So along comes the boron. Has its R groups here. Then it has the hydrogen here, right? And let's get our red color, right? So what's happening? Oh, no, hold on. Let's I guess let's not get ahead of ourselves. So what's happening here is that one of these bonds is going to go up here.
Do a proton transfer.
Yeah, and then the hydrogen's going to go down here.
Okay.
And what that ends up looking like is right, when we have that hydrogen came off of that boron. So we have that.
So it was a proton transfer to getting the H, and then the RRB negative attacked, nucleophilic attacked the
Yep.
now double bond effectively.
Correct.
Okay.
So what else do we have in here? We have hydrogen peroxide and we have sodium hydroxide. So the sodium and the hydroxide are going to dissociate. And we have our peroxide, which we know is unstable. And so what goes on there? This negative charge comes in and attacks, and then that bond goes to the oxygen. Right? And what have we formed? Water.
Yep. And NaH.
So one of the things coming off of there is H2O, because the hydroxyl group steals a hydrogen. So it forms H2O.
Isn't that a peroxy acid or something? Or no?
No, but now we have a radical, right? A peroxide radical.
Oh.
And let's scroll down a little bit. Can I? No, I can't. And so then we now have OOH, right? It's missing that. And so it's going to have
charge.
And that sodium is going to, come down and say, oh, hey, I like you. It's going to hang around there. Now, I'm not necessarily expecting this level of granularity with, the carrying over of the sodium and stuff like that. I'm doing this because I don't think we've quite gone over it in this detail, so I want to show it to you. But that's what's happening here, right? So now we have this peroxide radical, and it's going to attack this molecule here. Okay.
Yeah.
So it's going to come in and it's going to go right there.
Yeah.
Oh, so we don't really worry about the sodium attacking it then? The peroxide?
The sodium is like a spectator ion, right?
Oh.
It's there, and it's going to go wherever it kind of detects a negative charge, and it might bond with the hydroxide again if it's liberated and it's free. It's just going to kind of be in that initially to get that hydroxide ion to pull off that hydrogen to create a peroxide radical.
Okay.
So with this going into here, now we have a situation We have a situation on our hands where I might have to erase some stuff too in a minute. I'm running out of room. We have this. And then now boron has four bonds. And we know because we talked about boron and how it's, you know, unique and stuff, and it likes to have these 3 bonds. That's no good, right? So that's going to give it a negative charge. And so that sodium could say, oh, hey, I'm going to hang out with the boron now. It's, you know, it's kind of promiscuous. It's like, okay, now boron's my best friend. But that's not stable, right? So what's going to happen is that this oxygen, so the bond here, let's go to red. This bond here between the boron and the carbon, it's going to go here. And now this bond,
it creates a double.
Go here.
A double O bond.
Mm-hmm.
It creates that double O, or that bond, 2 bonds.
Yeah, so then what we end up with is yeah, the O sandwich. What's wrong? What's the matter? You went up? Okay.
Okay, so
You guys follow me here?
Yeah.
yeah.
And then this OH group that was cleaved off of that peroxide. Okay. Now that OH group
is gonna
come in here and attack the
kick
boron.
off the B. Kick that off.
And we're going to end up with, that's how we remove that Br2. So we get B. Oh. Sorry for the background musical here. Br2OH. Okay. I'm going to erase now if that's okay.
Can you hang on 1 second, please? Or I guess I could just rewatch this later. You can.
No, let's hang on.
Is that double bond right there below the oxygen on the bottom here? Is that connected to that? Like, there's a carbon after that oxygen, right?
Yeah, sorry, it's a little smushed, but
No,
that
it's
oxygen
okay.
took the place of this boron bond, right? So the oxygen is now bound to that primary carbon.
Oh, okay. Oh, okay. All right. Okay. Thank you.
You'll have the double bond there.
Okay. Hold on, I'm almost done. Okay, then. Br2OH.
Okay?
Yeah.
All right. No rush. All right, so if we take off this Br2, what we are now left with is an oxygen that is bound to that carbon. But now it's not particularly happy, right? Because it only. What? What do you want, baby? What do you want, Nora? Mama? Yeah. Yeah, Mama's working. I know. I know.
No.
You want something to eat? Okay. All right. Now what I want you guys to do while I get Nora something to eat, I erased it, but remember what one of our byproducts, when that hydroxide, if you look back up in the higher up in the reactions and the mechanism,
H2O.
we made H2O when we took that hydrogen off, right?
Oh,
So
yeah, yeah.
H2O is now in the mix.
Because now this is the enol, right? Effectively.
Hmm?
We're at the enol step. And now we're forming it into an aldehyde.
Correct. Correct. So what happens when that thing interacts with water? Let's teach you something to eat. What do you want? Oh, I know. Mom's not here. You want some? Yeah. Can I put you in your chair? Okay. All right. Give you some more raspberries. Okay. Well, I'm looking forward to spring for more than one reason, but hopefully illness will be less rampant among the Franz clan here. Okay, so if this molecule actually looks like this, then what we have is, let's get to my red here. We have this go in here. And this here. And of course, that sodium is still around, right? If we wanted to be complete. But,
Now you're going to form the NaOH again.
yes, no.
Oh.
So this we put an H on there, right? So the enol, remember an enol, alkene, all alcohol.
Huh.
And as Ian pointed out, when we pulled off that hydrogen, we created an OH group, which then comes back to its old pal. You know, it's like long lost lovers. They had to break up and they had to, you know, date and you know, you choking? And, you know, test the waters a little bit before they realized that they had a good thing all along. You okay? All right.
How sweet.
Hey, it's Valentine's Day, right? So,
I don't want to hear any of that sweet crap.
happy commercialized day of love. Hallmark
Now,
moneymaker.
Day of candy, and so I had to buy candy for my family, as if we don't have enough.
Right. This is like Valentine's Day is like Halloween 2.0 at our house. Basically.
Yes, same. It's outrageous.
Yeah, my wife and I, we don't even celebrate it. Okay, so now we've got this situation here, but remember, it's going to tautomerize. Say that 5 times fast. Let's go to the red, right? This hydrogen, or well, here, there's a bond here. Darn it. Should have drawn the bond. There we go. There's a little tiny bond. That's going to go to here. And the double bond is going to move up here. and then we would write it with, double arrows. And it would be creation of the aldehyde, right? Because this is a hydrogen right here.
Yeah.
That's a lot, right?
Yeah.
That's a lot going on there. But not as much as if it was BH3THF, right? So
Yeah, there's a couple more steps.
yeah, babes.
1, 2, 3. 1, 2. Okay.
And again, the key is up, right? So I could go right here and show you. I used Cam Scanner for the first time because I was at home. I was planning to, scan this at work and stuff, and my printer's not working, so I got to ink and stuff. So, oh, you're kidding me. Did it just
Only scan page 2.
well? Clearly, this is my first time using Can Scammer. Yeah, it's Can Scam.
Well, at least we found out now, so that's okay.
No,
All right, well, I'll
you got it
rectify
right.
that. I'll fix that and figure it out. But I
Okay.
have it written out, and I'll resubmit that.
It's okay.
All right.
Well, that one's, I mean, it's not, I mean, it's really not that bad if you just kind of think about where things are going and just kind of what the other things can interact with and what everything, if you think about everything that's in the solution all the time and then what can just keep interacting, then it's not that bad if you just keep following the sequence.
No, yes, I'm glad you see it that way. It's not that bad. I mean, it is a
Not
lot
too
of
bad.
steps. And
Yeah.
Here's the thing. If you miss a step, is the whole problem wrong? No, right? I mean, not to me anyway. I don't know, Ian. If if your former OChem professor, if he gave you partial credit or what, but like these are each 10 points, right? It's not all or nothing. I don't think that's fair. For here too, right? So this now I just realized this is the exact same molecule, I think, looking at it, as the practice problem that we did for this. Where was that? Allylic bromination. Yeah, right here. It's just flipped. Okay, so we've literally already done this one in class before. This molecule got flipped around. So what does that look like? Well, N-bromosuccinimide is going to
That's just giving the one BR, right?
exactly. It's allowing us just to have free radicals. It's preventing the liquid bromine that doesn't radicalize if we were just to use BR2 and shine it with UV light. It doesn't give us a mixture of products, right?
No,
When we see light,
free radical.
when we see light, we could assume a free radical.
Yes.
Yeah.
So this asks for, if you go back up, if you go to the previous page, it says something like, include the initiation, propagation, and termination steps if you have a radical, right?
Oh, yeah.
on the exam on Thursday, if there's a radical, you'll probably have to keep this in mind, right?
Mm.
That's NBS. And remember, with free radicals, we draw the fish hook, right? Just one-sided arrow to show one electron moving, not both of them.
So then this is propagation.
Well, this would be initiation.
Oh yeah, that's what I mean. Yeah.
So let's. Initiation. Okay. Forgot to change this before. All done? Okay. You want to draw? You want some more? Okay. You're gonna eat them all. Okay. So then, in the presence of more light and heat, right? We're gonna have and this, we symbolize a radical with the dot. And then we have what we were wanting to get all along, bromine free radical. Now, propagation. We have, what is our thing? Okay, it's this. Yeah, yes. Right. And what is it not showing? It's not showing a hydrogen there. And then we have our free radical. And that's now going to here. This goes here. And this bond goes here. Okay. We've pulled off a hydrogen, but we've only pulled off one electron. So the other electron goes to the carbon and we create the carbon free radical, right?
Oh, okay.
So that is going to look, that's going to give us HBr, right? Because now they're happy. And the carbon free radical. Okay. Whoops. So I'm going to erase the initiation now. More.
And then, yeah.
I'm sorry. Is that okay if I do that?
Yeah. So then now we're not too worried about the rest of the NBS molecule once it's the radical that it is.
Yeah, it's done. It's done. And
we don't need to keep.
And I'm not. You know what? If you have NBS as a mechanism, I'm not even going to expect you to draw out that molecule. You could just write.
You can just write propagation as creating one BR radical.
Initiation and write BS.
Yeah.
Or maybe just draw something and write the bromine and just show that it goes and creates a bromine free radical.
Okay. Cool. Okay. Cool. I mean, I could write BS all you want. Sorry, that was low hanging fruit.
you know.
And so now the
Easy.
next step would be that we can create the bond can shift.
Yeah, well, so what else is happening, right? So we have Br, free radical, attacking the hydrogen of that alkene. What else? We have that radical going back, you know, eventually it's going to terminate, right, by meeting up again with the rest of that N-succinimide, right? Yeah. We can also have this. Two bromine radicals
Meeting together.
coming together to form Br2. Okay. All this is happening at the same time, right? Together. And
so won't one of those bromine free radicals go in and attack the free radical there where the carbon is, the carbon free radical?
Yeah, well, yes, that's where we're heading.
Oh, okay.
Oh, what do you want? Do you want back in your seat? Oh, well, you stood up. How dare I? Okay. Okay, so what, baby? What is it? Mm-hmm. I don't know what you want. Mama's working. Okay, so what else? This
and wait, so that and then that last propagation though, you would say Br squared is termination.
For termination,
that's one product that can be a terminant, like a termination.
What we would have is in our termination, essentially we would have, let me write it up here. I know, Mama's not here. Termination. We would have our radical.
Keep going. Go on.
Okay, and am I red? Yeah. Whoops. Whoop. Right?
Cool.
Yeah.
And then please allow me to kind of move up to this part here. It would look like
yeah, cool.
okay.
Okay. That looks good.
Yeah, awesome. The last one really isn't that. Well, that's Bennett. Do you want a flower? Do you want a flower? No. All right, one more. You want this? No, you're gonna ruin that. That's Bennett's picture. You want banana? You want a banana? Okay, we get her a banana. So, other thing we could do. So, Ian, we discussed this, I think, beforehand. The lab is going to be another bromination, but it shouldn't be very long because there's no reflux.
Okay.
And so Mariola will be there to help in any way, and I'll be on Zoom. So if we want to go over some more of the exam, since it's going to be a short lab, I'm happy to do that with the other stuff. I wanted to focus on these mechanisms and stuff first, because clearly it's taken a lot of time. Oh, you want the whole banana? Oh, okay. You're a big girl now. No more sliced banana. She needs to. Here, you want me to take it out of the? Here you go. There you go. Oh, okay. Here you go. My goodness, trying to figure out what someone who is old enough to have a lot of strong desires but not communicate them is incredibly frustrating. All right. So, and again, I apologize for all the distractions, guys. But,
Okay.
all right. Let's do this last one. What's happening here?
Acid catalyzed reduction.
We're taking that alkene.
Yeah, we're adding an OH.
Adding an OH. You don't want this, Nana?
And there can be rearrangement. And in this case, there will be, I assume.
Let's see.
Because you want it at the tertiary.
So what you're saying is that we'll end up with this product. Nana. Oh, you want to feed me the Nana? No, well, you eat it then. Okay. Like that, right? Even though the double bond's up here, it'll rearrange to get to that more stable tertiary carbon.
Yep.
Yep. Okay. Okay. So let's write that out. Let's see what that looks like. Yeah, what's wrong with that, Nana?
Oh yeah, it's plus an enantiomer, right? I guess technically. Or is it? It can be both in and out.
Right. So, because you have this methyl group here, it would. You don't want this? You want me to eat it? You want to go? Okay. And I don't think there'll be an enantiomer because it's just like flipping over the molecule.
Through the chair.
Yeah.
Okay. It's just
Which side will the hydrogen tack onto? The side closest to the tertiary carbon, or the side farther away, huh?
Well, so that's what we'll get. Goodness, that's what we'll get to.
Okay.
Okay, you all done? So we have this happening.
Yeah, so proton transfer.
Yeah, because it's the electrons in the double bond attacking the hydrogen, not the hydrogen attacking that. So, yeah.
Remember, there's a hydrogen here, right? We didn't draw that in the skeletal structure, but what that's going to do is that's going to put a charge right here, right? We're going to have a carbocation on a secondary carbon.
Yeah, so, okay, so it's like the back of that double bond there. The back of the double bond attacks the hydrogen, not the front. So that creates the carbocation next to the tertiary carbon, not in the back, not behind it, not to the left there.
Right.
Okay.
Yeah.
Close as it can, and then it's going to move over.
Now there's the hydride shift.
Yeah. So this is going to go here, and the hydrogen is going to go there. And then what we'll have now is the carbocation on a tertiary carbon.
And then we have plus water now.
And that's how the OH group goes on there then. Yeah, okay. So
Oh God. Okay. You don't want the sliced bananas anywhere in your vision? Is that what it is?
Get them out of my sight.
Okay. Plus H2O.
Now that
And
nucleophilic attack.
what, baby? What? That? What do you want? Almost done here, guys. I don't know if I'm talking to you or myself. But
You got great.
effectively, here, let's I can give myself some more space if I move this over here. Close. There we go. Cool. All right, so now we've tacked on a water.
Yeah.
Yes.
Now we need to take one of those H's.
And now this is charge. All right. And then we have another H2O. Right. And there are some lone pairs. That is almost there, okay? That's going to come in and take that hydrogen off. Those will be lone pair on the oxygen. And we get this. Okay. You have a stinky diaper?
Okay, cool.
Okay. Well, good. Look at our friends.
I'm sure you're not going to give. Hi.
Hi. Say hi.
I'm sure you're not going to give us one this easy on the exam, though. So, but it's good that we know the process.
This is still a legitimate practice.
Yeah, true. Yeah.
Travis, yeah. I mean, I'm not out. I'm not out there to try and mess you up.
Carl's here just to make your life miserable.
I think tests with Bruce and Larry over the years have really scared me. So
I don't want you to be fully prepared in terms of knowing what to expect. Okay. Yeah, there might be different mechanisms. Maybe it'll be this. Like I said, I haven't finished the test yet. So maybe it's the same reagents, different molecule, right? Regardless, we see these over and over again, right?
Yeah. And I do know the process a lot now. So, I mean, even if you do throw other things in there and make it similar, I mean, yeah, if it is used a lot, acid catalyst, the acid catalyst, then yeah, I mean.
Yeah, each one's so important. Well, and then instead of doing this, it could have just been adding a methyl, which is effectively almost the exact same process. You're just not tacking on the OH and then pulling it off.
Yeah, if we had
like a methyl shift.
Yeah, or if we had methanol in here, right? We could create an ether, right? Depending on things. But so it's important to see what is over that arrow and what isn't, because that will steer you in different directions potentially, right? Like this. Is this what you want?
So is that kind of a rule of thumb? Like if there was methanol in there or ethanol, then that would create an ether. But if there's water or hydronium, then that creates an alcohol. Is that kind of a general rule of thumb? Not with all things, but with
Yeah, so if we, where was it? Oh. I mean, yes, you could say it's a general rule of thumb. Now, will we see that, tacked on to all of these mechanisms? No, not necessarily. It depends on what the other reagents are that are in combination with that.
Yeah. Okay. Yeah.
But yes, if you see an alcohol in this case, like remember last quarter we talked about there being alcohols in there as part of the solvent. We're not going to include them in these mechanisms because they're just a solvent, right? If they're in there, they're going to be doing something.
Okay.
Ethyl group, methyl group, or propyl group.
Okay.
Because is that just if it's an OH, then it's a protic solvent? It can give H's or something?
Yeah, so
with an ETOH, the OH is a protic solvent, I guess.
aprotic.
Aprotic. Yes.
Yeah. It's not giving off.
Yeah.
Right. So then it gets back into those rules, and now we're talking about some stuff from first quarter that may come back. We may have to
probably, I assume, because I think protic and aprotic is probably very important.
Well, we'll get into synthesis after this. So you're learning all of these things to, synthesis is kind of the main goal, right? We are synthesizing molecules in these exercises, but we're studying them kind of in isolation. So we'll start putting together more things after the midterm, which is that last question, which is not going to be on the midterm, right? We haven't covered this yet. I didn't get to it. So the synthesis question won't be there, but this is what I'm talking about, right? We'll start putting things together and creating a bigger story, right? To getting our products that we want. Okay. Any questions? I know that we didn't go over any of this top stuff. Like I said, that will be once I figure out how to get my cam scanner correct. That will be in the key. If you want, we can go over this. Hopefully, I'm going to try to put this kiddo down for a nap in between now and lab. And so, we can do these questions as well if you want. But I feel like these are pretty straightforward. If you have the answer key to this, you should be able to kind of figure out, if you don't already know on your own, where that came from in terms of nomenclature, right?
Yeah.
RNS, cis, trans. Here, you guys, I'm pretty sure by now know what a primary carbon is. Yeah, it's going to be this methyl group, this methyl group, this methyl group. Right? This is a quaternary. So I don't know if can you see my cursor that's moving around, or am I just doing this to myself?
Yeah, I can see it.
Yeah. Secondary. Okay, thank you. And then this is the tertiary. The tertiary is going to have the lowest bond dissociation energy, right? Because quaternary isn't going to dissociate
at all. Yeah.
And this is the most stable. So. And then here, I think we've covered all of these things. Like a benzylic, for instance, benzylic is going to be a carbon that's next to a benzene, right? So if you said, what's a benzylic? It's going to be this tertiary carbon here, right? You guys know what ketones and epoxides are, I think, right? Halides, enols, aromatics. One thing, allylic and vanillic and aliphatic. You guys I don't know if we've covered aliphatic.
We didn't cover that. No.
We didn't cover aliphatic. Okay.
Uh-uh.
So let's aliphatic. What would be an aliphatic? Aliphatic. Would be here. It's next to a vanillic. Oh, I'm sorry, allylic. Allylic is next to, so a
allylic. This one's allylic, and there's two, right? One on both sides.
Yes, this is allylic, and then this is allylic.
And those two with the double bonds are vanillic.
Vanillic, right. And Travis and I were discussing all of the vinyl chloride gas that was released in the train crash in Ohio, if you haven't heard about that. PVC, yeah, PVC is very stable, but vinyl chloride, not in polymer form, is very toxic. So it's pretty terrible. But aliphatic are just basically hydrocarbons. Okay, so this right here, this would be aliphatic here. This would be an aliphatic here. It's not adjacent to a vanillic or a benzylic. Okay.
Oh, so the two on the very end you're saying are aliphatic?
Sorry, what's that?
You're saying the two on the very end are aliphatic?
Yeah, so I'm saying that this is an aliphatic because it's not adjacent to any alkene, right?
Okay.
This is an aliphatic, and this is an aliphatic.
Oh, and yeah, okay. Not adjacent to any alkene.
So then the
vanillic,
on the first one too, the two primary carbons are also aliphatic after the aromatic ring.
Yes, this so aliphatic. Oops.
Yeah. Okay.
Oh, good question. Yeah.
Aliphatic.
Yeah.
This, so let's get a different color for here. This one is benzylic, but it's adjacent to a benzene ring. Okay. And then the benzene ring is aromatic.
Aromatic.
Right.
And we don't need to say like inside the aromatic are
no.
Okay, that's
when you have a cyclohexane or cyclohexene, we can just say that's benzylic.
Okay.
Here is a free radical. What's this?
Aldehyde.
Aldehyde. Yeah.
And what's this?
Ketone.
Ketone.
Exactly.
And so that's not an aromatic, right? Because there's no double bonds on the inside.
Right.
Correct.
It has to have those 3 double bonds.
Okay.
Really some.
Would those then also be aliphatic?
No, not in the ring.
Okay. So if they're in a ring, they're not.
Yeah.
Okay.
Yeah, you wouldn't designate this as aliphatic.
Yeah.
Okay.
Sleepy? Yeah.
Yeah.
He's tired. Yeah.
Oh, you're talking to her. I thought you were talking to me. Yeah, I'm sleepy. I'm just kidding.
Are you sleepy, Travis?
Yeah, I'm sleepy. Yeah.
Me too. We all need
nap time, everybody.
All right, well, get a nap in at 1 o'clock. Mariola will be in lab. We're going to try to take some bromine and mix it with some still bean. So it's not Jim Beam. Still bean. It's an alkene that I'm hoping will crystallize and form a brominated product without having to heat. And I'm thinking that without having to add heat, we can prevent that sludge that we made. Okay.
Here's to hoping.
Here's the fingers crossed. and my wish is that we get that far and then we vacuum filtrate to get our crystals. And then, we can, depending on time and availability, we can recrystallize it, or we can take a melting point. We could also, do that. We could spend some more time going over the exam with these first parts. But again, unless you really have some questions on this, I think it's pretty self-explanatory. You can always, ask me a question via Canvas, and we can hop on Zoom if we need to and go from there. I'm hoping Critter will be back in school tomorrow, and I will have office hours from 12 to 2 in that case. But if she isn't, I'll still do office hours on Zoom. Okay.
Thank you, Carl.
Thanks, Carl.
Yeah. So this is recording. As soon as it's done, processing and stuff, I'll upload it to YouTube, and then I'll put that link in on week 6. Okay, and then I'll figure out what I did wrong with the cam scanner, and I'll get the full key to replace that one that just has page 2.
Okay.
All right. Hang in there. I'll see you in an hour.
Okay. Thank you. Later.
Thanks. Bye.
Bye. Bye. Bye.
Bye.
Oh.
Bye.